So let's talk about a few things first. As soon as I get my clicker going. All right. All of you, I think all of you did. I'm still working on putting the grades in for the first two sections of notes, but you should have taken notes on the first two sections, okay? Do you remember anything just standing out to you early on from your notes? Is there anything that you felt particularly important that you felt, I got to put that in my notes? Okay, so anyway, I had expected that. I wasn't really, I was just curious because you never know, someone might have something to say. But chapter 6, we are talking about the electronic structure of atoms. We are, for the most part, finished with reaction chemistry, okay? And I've been talking about chapter 6 for, feels like a while now. And I've been saying every time that, we're shifting away from reaction chemistry and we're now going to start focusing on atoms themselves, okay? Because since we just got done with reaction chemistry, we got to figure out why those reactions either occurred or didn't occur. And that's kind of where we're going to be spending for the next few chapters, okay? This one, we dive deep into the entire structure of atoms. We get to learn about our little itty bitty buddy, the electron, and just how weird the electron is. As we progress through this chapter, it's one of our last long chapters. There's like 9 sections in this chapter, okay? We're going to spend a great deal of time talking about chapter 6 over the next coming weeks, okay? There's a lot of stuff on here that I like to put practice on. Now, I did tell you that compared to other chapters, chapter 6 is very much smaller in terms of math. But again, there's still an eensy, beatsy bit, okay? And some of the math that we're going to get into, again, the very limited math we get into later on in this, I see about the second half of the chapter. It's kind of, I guess the word I'm thinking about is thought-based, okay? But it's all pattern, there it is, pattern-based. Okay, so we're going to spend some time on that as well. But this is going to be a weird chapter in terms of content because the atom and the electron in particular is weird. And so we need to first talk about a few things before we really get into understanding the atom. Okay, and that's when we start talking about wavelength and frequency. That should be a term that everybody recognizes. I know they do because we teach it in intro. Okay, so we're going to focus on that in what's called the electromagnetic spectrum. And that is something that you are going to have to know throughout this chapter. And I have a great practice tool for you to help you remember that, okay? So first, let's talk about waves. Because as we start talking about the electrons specifically, we're going to learn about what's called the dual nature of electrons. And one of those natures of electron is waves. And electromagnetic waves travel throughout all sorts of media, environments, okay? So let's talk about wavelengths, okay? We're going to be talking about electromagnetic radiation. The distance between corresponding points on adjacent waves is the wavelength. This little symbol right here is called lambda, okay? So, again, you could go from peak to peak, trough to trough, side to side. Any two corresponding points on neighboring waves is the wavelength. Now, the number of waves passing at a given point per unit of time is called frequency, and we usually measure this in terms of a second. How many waves are passing a particular point in a second? For waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. So, reading that last bullet point, what type of relationship do frequency and wavelength have? They have an inverse relationship, okay? Where one is big, the other is going to be small. If you have a really long wavelength, meaning you have a really far distance between two corresponding points, you're not going to get that many waves through that given point in a set amount of time. But if you go the opposite way, if you reduce the wavelength size, you get more waves into a certain area over a period of time. So you have to think about that. Okay, that type of relationship of frequency and wavelength having an inverse. And this is not V. Okay, this is another letter called nu. Okay, so we're going to be using lambda and nu to help us calculate a few different things. Now, what's nice about electromagnetic radiation is all types of electromagnetic radiation travel at the same velocity, which is at the speed of light. Now, it's really in the same velocity in a vacuum, but a lot of our stuff in this realm is done by looking at a vacuum. You need to know this number, okay? 3.00 times 10 to the 8th meters per second. That is how fast all of our electromagnetic radiation travels, okay? You're going to see, and I'm going to point it out when we get to it, for some reason, you've experienced this book. Every once in a while, the book throws a slightly different value than what it typically uses. You'll see that it says, like, when we do a calculation, it says like 2.99 times 10 to the 8th or 2.998 times 10 to the 8th. Can't remember which one it was. Don't do that. Just do 3.00 times 10 to the 8th meters per second. Therefore, the speed of light is known as c. C is equal to lambda nu. So if we multiplied the wavelength and frequency of a particular radiation, it would equal the speed of light. But since we know that they all travel at the speed of light, we have basically a constant variable. So where, if we know one of these two variables, we can calculate the other. Okay? Now, the tool that I use is a song. But since I am recording this session, I'm going to wait until the very end of our discussion today to play it, because I don't want a copyright strike. So I'm going to turn after we get through everything, I'm going to turn the recording off, then we'll play it probably twice, because it is awesome. And I guarantee you that when this earworm gets stuck in your brain, if you sing it around anybody who's had this class before, they will join you wholeheartedly, because it is that good. All right? But there we go. I can't, copyright strike! Okay. You know what a copyright strike is? Okay. If you don't know, it's when you basically play copyrighted music or other items without written consent or permission from the owners of that. And so I'm not going to do that right now. Anyway, this first practice problem does not involve any calculation. Okay? We simply have to start thinking about wavelength and frequency. And I know you should be able to see this in your notes. Okay? Now I'm going to refer to these as B and A. I know they're backwards, but in the question, and I left the solutions up here, it doesn't match. It doesn't match these images down here. So let's talk about this. So we have two electromagnetic waves that are represented in the margin. Well, again, see right there. They're not in the margin. They're down here. Okay? Which wave has the highest frequency? Okay, let's start there. Looking at these two, which one do we say, left or right? Which has the highest frequency? What's that? Left. Why do you say that? Very good. The wavelength is shorter. There's also something we're going to write something on our notes from like 2 slides ago. I'm going to do that before we get to the video. Okay, very good. Question B, if one wave represents visible blue light and the other represents infrared radiation, which wave is which? Well, now, hold on a second. That's nothing that we can necessarily look at. So we have to look at the spectrum itself, okay? We see red is here, blue is here, okay? Now, I'm going to write something on here, and I want you to do the same. Long lambda, which is wavelength. If you want to put lambda equals wavelength, just to always keep reminding yourself, wavelength, there we go. So I'm putting long wavelength on top. Small frequency on bottom. And I'm going to also write on the left-hand side, but just kind of the opposite. This is small wavelength. Large frequency. So, picking these two wavelengths right here, okay? Which one of these would you describe as blue light? Which one would you describe as red light? If red's closer to the side, because of this whole electromagnetic spectrum, the visible light portion, what we see, is very small. So, which one has a long wavelength? Which one has a high frequency? Any guesses? Well, since the red light is over here, closer towards the long wavelength side than blue is, I would say that the red light more closely represents this wavelength right here, because it's got a longer wavelength in comparison to this. Therefore, blue light being further to the left, closer to a large or high frequency, it's going to have a shorter wavelength, but it's also going to be at a higher frequency. So this right here is going to be what we are going to ingrain in our memory over the next few weeks, okay? Wait a second. Oh, I totally messed that up, didn't I? I was a question ahead. Golly gee willikers. So what I just did was I answered the practice exercise, talking about red and blue light. Not bad. So let's actually go back to the question at hand up here. And I left the solution down here because it explains it pretty well. Okay, it says, again, going back to the red and blue light question, expanded visible light portion, which is this, tells you that red light has a longer wavelength than blue light. The lower the lower wave has the longer wavelength right here, and would be red light. Let's go back up to B here. Let me read that again. If one wave represents visible light and the other represents infrared radiation, which wave is which? Here's infrared. Here's visible light. Okay, infrared, visible light. Which one would have the longer wavelength, infrared or visible light? Now that we've kind of talked about this a little more. Both. Infrared, why do you say that? There you go. Easy enough. It's farther to the right of visible light, therefore it's closer to having a longer wavelength. So that'll you'll get this down. But right now, I need you to get your calculators out. Let me see something here real quick. Okay. And I'm going to do this on the board since I don't have anybody on my Google Meet. It's been a while since I've done this on the board. You know what? I'm going to do it on here since I am recording. Sorry. Okay. So you'll notice that I've got this up here. I just noticed that for some reason I think it's missing from your copy, and I don't know why. So I had to put it back in hastily the other day. So I'll talk to you about that. So we're going to, this next sample exercise, we're going to be using that equation of C equals lambda nu. So here this question says, the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. Okay, what is the frequency of this radiation? Well, what do we know? First off, we know that, I'm going to come down here. First off, we know a few things, okay? We know that the speed of light is, what's the number for speed of light again? Very good. You can't see that. There we go. So 3.00 times 10 to the 8th meters per second. The question says the wavelength is 589 nanometers. Okay, so lambda is 589 nanometers. Here's something I also want you to write down. Wavelength must be in meters. And it makes sense because of this. Okay, since the speed of light is a constant, and it's got the unit of meters, and we're solving for frequency in this case, we've got to make sure that we can cancel out those meters. Does anybody know, or off the top of their head, what units frequency is in? And that's nu. That's the symbol for frequency. We report it in hertz, Hz. We could also report it as this, s to the minus 1. Because when we are talking about frequency, we're talking about how many waves do we get per second. And in math terminology or math practices, when you have something like the unit to the power of 1, what that really means is something over s, okay? Per second. Or you could write it as s to the minus 1. Or you could write it as hertz, okay? More often than not, you're going to see it written like this, okay? I just wanted to show you what this was equal to. So we need to figure out what our frequency is. Now, you could, excuse me, you could convert it before you even get in there, or you could do it like they do here, okay? But what was I going to do? Oh, yeah. So there's a couple different ways. All it is dimensional analysis, okay? So in order to convert nanometers to meters, put that up there. Put nano is 10 to the 9th. Okay. And so nanometers cancels out. And then really all I have to do is get 5.89 times 10 to the negative 7th meters. Again, a couple different ways you can go about that. Okay. So now after I've kind of walked you through this stuff, we have the formula of C equals lambda nu. So in order to solve for frequency, I'm going to divide both sides by lambda. So now I'm going to get nu is equal to C divided by lambda, which is going to be 3.00 times 10 to the 8th meters per second over 5.89 times 10 to the negative 7th meters. And so if you were to calculate that, and I want you to calculate it just to check this, but according to the book, you should have, oh, you can't see that. Here, I'll write it down because I don't know if you're going to be able to see that or not. 5.09 times 10 to the 14th s to the minus 1, or you could also write it as 5.09 times 10 to the 14th hertz. So here's your answer, just shown in both ways. This one, 3.00 times 10 to the 8th meters per second. That's your speed of light. So let's do a couple questions here. All right, so let's look at practice exercise down towards the bottom. Let's look at A. A laser used in eye surgery to fuse detached retinas, sounds awful, produces radiation with a wavelength of 640 nanometers. Calculate the frequency. Well, alrighty then. Well, we already know that C is a constant, 3.00 times 10 to the 8th meters per second. Says the laser has a wavelength of 640 nanometers. Again, I'm going to go ahead and convert before I even put that in there. 1 meter. What was the value of nano again? Very good. 10 to the 9th nanometers. So what do you get when you convert that? Very good. You're going to find out that that's going to be a fairly, it's not an actual constant number, but a fairly normal conversion value right there. 6.40 times 10 to the negative 7th. Okay? And we're trying to find frequency. So again, for practice, wow. We write our formula. I can write that a little bigger, actually. C equals lambda nu. Again, solving for frequency. Going to rearrange it to where its frequency is equal to C divided by lambda, or 3.00 times 10 to the 8th meters per second over 6.40 times 10 to the negative 7th meters. I want you to calculate this and provide the correct unit in your answer. Whoever answers is going to be super famous because it's going on my YouTube channel. Don't hold back. What about you back in their window corner? That's why we do this. Okay. Might be going the wrong direction. So, what are you when you put this in your calculator? Are you putting it in parentheses? Okay. So when you put it in your calculator, do it like this: parentheses, 3 times 10 to the 8th, close parentheses, divided by, open parentheses again, and then write that, and then close parentheses, then hit equal. Sometimes you kind of have to, what I call, trick the calculator into knowing what you're trying to do. As handy as they are, you still kind of have to work with them. I'm going to stick with you. I didn't say anything. There you go. And what unit am I going to put on this? That's the -1. Don't forget that to the -1. Or you could put hertz if you want to. Okay. Yeah, seconds would not be a correct unit. It's got to be s to the -1 or hertz.
Why is it S?
Because the s to the -1, like this I just had, really means in math terms that it's on a denominator. So that means per second, which frequency is the measure of how many times a wavelength passes per second, or usually. Okay? Let's do one more practice problem here. And that is back here in your notes. Oops. And that is question B. An FM radio station broadcasts electromagnetic radiation at a frequency of 103.4 megahertz. And it tells you that a megahertz is equal to 10 to the 6th. Calculate the wavelength of this radiation. The speed of light, see there it is. Speed of light is 2.998 times. Nah, no, we're not doing that. We ain't doing that. I think why they did it was because of the frequency is 103.4, which is 4 sig figs. There's your favorite term. Getting ready to do that again in intro here starting today. But just keep it at 3. Okay, just keep it at 3. So getting back at it here. Okay, so again, C is equal to, excuse me, 3.00 times 10 to the 8th meters per second. Frequency this time is what we know. It was 103.4 megahertz, which really boils down to 103.4 times 10 to the 6th, s to the -1. Again, I just changed hertz to s to the -1 since we're using it in the calculation. We need to make sure it cancels out the appropriate unit. And mega is 10 to the 6th. So that's where that came from. Okay. And we are trying to find lambda. So C equals lambda nu. We rearrange it to solve for lambda. This time we're going to have C divided by frequency. So again, when you put this in your calculator, you're going to need to use parentheses around everything. You're going to get 3.00 times 10 to the 8th meters per second divided by 103.4 times 10 to the 6th. If you wanted to make it 1.034 times 10 to the 8th, it's all the same. Okay, so go ahead and calculate that. Who wants to be YouTube famous? Pink calculator all the way in the back. And what's your unit? What's left if we... Very good. 2.9 meters. So for this particular radio station, there are 2.9 meters, almost 10 feet, about 9.5 feet or so, give or take a few inches of distance between each wave. So there you have it. There's your first, or not your first, but it's probably been a little bit since you're experienced with frequency and wavelength. But for now, I'm going to stop the recording so that I can share this wonderful music.